Hey everybody, this is Mr. Piercy, and what we're going to be looking at today is a relatively unique uh, section of properties related to circles. Specifically, we're going to be looking at some angle measurements related to circles that they may or may not be something that you will see on a like an SAT or ACT kind of college entrance type exam. It's even inside of circles, it's a fairly obscure topic, but it is something that uh, is there. So we do need to kind of cover it here. Here we're looking at angles that are either going to be inside a circle, on the circle, or outside of the circle. And here, this is where we're looking at angles on the circle. So here, theorem 10.11, you can think of that really as angles formed with a chord and tangent. You can say that. Angles formed with a chord and tangent theorem. This is very identically, or I'm sorry, not identically, but essentially this is the same concept of what we saw with inscribed angles. With an inscribed angle, you have two chords essentially inside of the circle that create an angle whose vertex is on the circle itself. And what we established is that the measurement of the inscribed angle is going to be half of the measurement of its intercepted arc. Well, this is the same idea. Even though this is not an inscribed angle, there's just something about the angle having its vertex on the circle itself that causes it to have an angle measurement that will be half of its related arc. In this case, if you look at angle 1 inside of the diagram, angle 1 has an arc that goes from A to B. Well, the measurement of that angle 1 will be half of the measurement of the arc that would be formed. Because if we had the central angle here like that, whatever that angle is, that's the measurement of the arc. Well, the angle that we have at 1 is going to be half of the angle that is at the from the center of the circle there. So half of the arc also. That's kind of what we're looking at here. Moving on, this is just an application. Now that we understand what the measurement is, can you actually figure out what they are? So in example 1, or A I should say, we have measurement of angle 1. What is it? Well, angle 1 is going to be half of the 132, so you just say half of 132. And for part B, if we know the measurement of the angle, we can double it to get the measurement of the arc. So double that, and that's how we get the 66 and the 220 respectively. Now this one is a new one. I guarantee you've never seen this in any other previous math class before, and outside of maybe even this section, you probably won't see it. Now, if you haven't seen them already, there are a couple demonstration videos that I made that shows you why these properties exist. But what we're looking at now is we have a couple of chords that are inside of the circle, but they're not creating an angle that is like an inscribed angle. This is what we refer to as the angle. This is what I generally refer to as the angles inside of the circle. We have inside, outside, and on. So what we're seeing on this page is we see both the angles that are inside and the angles that are outside. The ones that we saw on the first screen, that was the angles that are on the circle. That's just how I classify them to make it easy talking about them in class. Well, what we see in the first one with the angles inside of the circle, the measurement of the angles formed by the chords will be equal to the average of the measurements of their respective intercepted arcs. So when we look at angle 1 has these two arcs that it intercepts, AB and CD. Well, the angle measurement is going to be half of the measurement of those two arcs added together. Same thing with angle 2. Angle 2 has a different pair of arcs that it intercepts, so we would kind of be looking at angle 2 with arc BC and arc AD. The angles outside of the circle, these are going to be formed with either secant segments or tangent segments or lines or whatever. secants or tangents. This one is a little bit less intuitive. If we were going to do an investigation about this in class, a lot of students struggle with the relationship of the numbers that they see here. Here, instead of saying we're going to take the average of the two arcs, we're going to take half of the difference. So it's not the average. We're going to take half of the difference of the two arcs. So the measurement of the angle that's outside of the circle will be half of whatever the difference of the bigger arc subtracted with the smaller arc is. So let's go ahead and see how we're going to work this out. All right, we want to know what's the measurement of the angle inside. What is the measurement there at x? Well, according to the equation, we're going to say it's half of the two arcs added together. So substituting the numbers and using our order of operations, add the two values inside of the parentheses and then take half of it, we would say x is going to be 126 degrees. Now, real quick, algebra skills. Let's say we have, what if I wanted to know something else? Let me just put this here because some of my students in class have been struggling algebraically trying to solve these things when it's not already isolated. So if I asked you to find the measurement of an arc instead of the measurement of the angle, could you do it? So here, I'm going to say the measurement here. Well, let's not say that. Let's just say x is equal to half of fj plus gh. Let's solve the equation for fj to make sure that we can actually do the algebra associated with it. Now, we could distribute the 1/2 into the parentheses and get rid of the parentheses that way, but personally I think multiplying both sides by 2 is easier in a lot of instances. So now I'm going to have fj plus gh. And now you can see if I want to get fj by itself, now I can subtract gh from both sides, so I would get 2 times whatever angle x is minus whatever arc gh is to be equal to fj. A lot of my students in class have been struggling algebraically if I don't ask them to just solve for x. So I just want to make sure, I want to demonstrate it and make sure you guys can do it too. Here, find the value of angle x. Again, we're looking at something on the outside. So we're going to say, in this case, the angle on the outside is going to be half of the difference of the bigger arc minus the smaller arc. Substitute your numbers, make sure you do your order of operations, subtract 72 from 170 inside the parentheses first, and then take half of it and get 49. And again, I'm going to real quickly just kind of do another one of these. Let's say I have angle x is equal to half of jf minus hf. Let's solve this for hf. Could you do it? Well, again, I'm going to get rid of the fraction by multiplying both sides by 2, so I'm going to get 2x is equal to jf minus hf. Move the jf over through subtraction, I'm going to say 2x minus jf is equal to negative arc hf. So now multiply both sides by negative 1/2 or divide everything, I'm sorry, not negative 1/2, but negative 1. Or simply divide everything by negative 1. And that would give me negative 2x plus jf, if we have my arc here, would be equal to hf. Or we could say jf minus 2x, like that. Okay, so just make sure you know how to, remember your algebra skills here because they don't go away. Here we're going to solve a real world problem. This is a really good application question, something that you probably won't do personally in your lifetime, but that's okay. Somebody at some point, I'm sure, had to think about it besides a textbook author that came up with a question. So here we have a plane that's flying around the world and we want to know what what part of the Earth can you see? Meaning from arc B to D, how much of this can you see? So there's a couple of different ways that we could figure this out. What we're looking at here that it's kind of letting you know here, it doesn't really say it so much in the problem itself, is that we have a couple of tangents. So that means because CB and CD are tangent to the circle, tangent to the radius, AB and AD, they form right angles, and so what we have are right triangles, meaning that we can use Pythagorean theorem, special right triangles for trigonometry, and that's really where this problem is kind of situated. We could also kind of figure out, well, what's the measurement of this angle here, and that would be the measurement of the arc also. Now, the way that they're kind of looking at it here is because the way the problem is set up, or the topics that we're talking about, we're looking at the angle outside. So we're really going to kind of say, oh, well, we have these right triangles again, okay? So what we want to do is here, we're looking at this as a right triangle. Because of the type of problem that we're working with, we're going to look for the angle outside here, and that will allow us to kind of do what I showed you a second ago. Can you solve for an angle, or can you solve for a measurement that's not isolated by itself? So what they're doing here is because we have an angle outside of the circle, we can now multiply it by 2, and that would give us, well, you don't need that anymore. We could take the angle that we get here and multiply it by 2 and get the whole thing. So then what we're really the way the problem is set up for us to look at, we're going to find out what this angle is here. We're going to find what this arc is here, and we're going to find with that, with this arc here and this arc here, we can find the arc that we're looking for from point B to D. So that's how we're kind of working this part out. That's why we're saying that angle BCD is going to be 174.2. Substituting our expressions, we're going to say, well, angle BED is going to be whatever, we don't know what BED is, that's what we're looking for, and BED is going to be whatever 360 minus that is. So that's why we're saying 360 minus x. So here, what I would do is, again, multiply both sides by 2, and then I would combine my like terms, and then divide both sides by 2x. So let me kind of illustrate what I'm doing here. I would say I would take the 174.2 and at this point I would multiply both sides by 2 and I would get 348.4 is equal to negative 2x plus 360, and then I would move the 360 over, which would give me negative 11.6 to be equal to negative 2x, and then you divide both sides by negative 2. And that's how we're getting the 5.8. Now, once you are good, go ahead and pause the video and answer these 4 questions here, and when you're done, go ahead and hit play and come back and see how your answers look against mine. All right. So finding the measurement of of arc ACB. Well, arc ACB is going to be double the angle that we see there, so we're going to say 2 times 120, and we're going to get our 240 degrees. Here we're looking at the angle outside of, where did I put my work? There we go. So I'm going to say the angle outside, GKH, is equal to the average of the 2 arcs. So we get x in this case. We're looking for the arc, so we're going to get x in this case to be 112. Again, find the arc, the big arc here in this case. We're going to say the angle outside is equal to half of the difference of the 2 arcs. So solving for y in that case should give you 82 degrees. This one here, I didn't work it exactly the way that they did before, because we know that essentially what I'm looking at is I know that this right here is a right triangle, and we know 2 sides of the right triangle. So what I'm looking at really here, so here's my right angle, C, E, and A, and we know that this is 6 and this is 4. Well, if I really want to know this arc right here, I would rather find the central angle here because the central angle and the arc are the same thing. So I'm going to use trig to find that angle here, and then I'm going to double it to get the central angle, and that's really what that's really the measurement of the arc that we're looking for. So that's one way that I thought that's how I worked out, but maybe not. Let me clear this out here so that way we can see everything. So here ACD, no, I did work it out the same way that the example did, I guess. But that's, thinking about it, that's really what I probably would have done when I tried working that problem out. Is if I can find the central angle and I want to know the measurement of the arc, well, the central angle and the arc are the same thing, so I would have found the angle that way. But here, this is what we're looking at. Find the measure of the angles that are either going to be inside the circle, on the circle, or outside of the circle. They each have their own unique characteristics and formulas or equations about how we find them. So if you have any questions about anything you've seen, these, by all means, let me know what they are. Until next time, thanks for watching and take care.